Hi guys, we'll get started in a couple minutes, just waiting for more people to come in. Does anyone have questions about last class? Okay, great. We will get started. Everyone can hear me, I hope. If not, just send me a message in the chat. At any point, you can tell me to speak slower. All right, so I've been working on an assignment for you guys that I said is due April 26th at midnight. So I will be posting it tomorrow, hopefully in the morning sometime, so that will give you guys a couple weeks to work on it. So for that, today I'm just going to finish off chapter 2, and then we'll do a bit of work in Stata. Okay, so yeah, that's the plan for today, and then you'll have a lot of time to work on your assignment, and of course, you guys will have lots of time to ask me questions. Don't feel afraid to do so if you have any concerns. All right, if there's no questions right now, we'll go ahead and start with chapter 2. Okay, great. I'm gonna share my screen with you guys then. Oh, not there yet. Okay. Okay, so we started chapter 2 on Monday, and we finished already our conversation about selection bias. I hope you guys had time to go through this equation on what we actually observe in differences in outcomes, how it can be a function of the actual treatment effect we're interested in, and the selection bias term. So I know it's really early in the class, so it's hard to start talking, but can anyone remind me what selection bias is? Anyone? Or what's an example of selection bias even?
Uh,
Anyone?
yeah, hi, Dios. I think that it's when you cannot observe the same person that goes to um well the last class you talk about a person that goes to the hospital and
Yes.
that you cannot observe if the person goes or not goes. It's like at the same time the effect that this person will have at the same time because that person cannot go or go or go.
Right. So what Helen said is that one person can only observe one outcome. So they can either go to the hospital or they don't go to the hospital. So it's impossible to compare both outcomes for one person. So when we compare two different groups of people instead of one to one person against two outcomes, then there's some sorting between the people because maybe the people who go to the hospital are going to be strategically different from people who don't go to the hospital. And that's because there's reasons for people to go to the hospital. So if I'm sick, I'm more likely to go to the hospital. People who are healthy don't need to, so they won't go. And so that's actually a difference in our outcome of interest because we're interested in how healthy the hospitals make people. So if it, from the very beginning, sicker people are going to the hospitals than healthy people, then our estimates are going to be biased because if we just run an OLS regression, we're saying, oh, there's a negative effect of going to the hospital on health outcomes. That must not mean that hospitals are effective. Whereas that's not actually the case. It's just the fact that sick people are going to the hospitals. So that's a selection bias because sick people are selecting into treatment. They're selecting into going to the hospital. So there's might be some characteristics that kind of determine treatment status. So being sick is determining whether you're going to go to the hospital, and it's also an outcome of interest. I think I got that. I'm confused. I kind of hate Zoom. Or someone messaged me, but I can't see it for some reason. Oh, got it. Okay, great. So that's what the selection bias term is. It's that there's some selection on a given characteristic that determines your treatment status. So then the treatment becomes kind of systematic. It's not random who gets treated and who doesn't. And when it's not random who receives treatment, then it's going to bias our estimate because then we're not examining the difference. We're not examining the effect of treatment on our outcome necessarily. That's also going to be combined with the initial difference between treatment status based on your given set of characteristics, right? So when we're trying to find the effect, to find causality, we need to get rid of that selection bias from our estimation, or else we won't have causality and we'll have bias in our estimate. Super clear, I hope. Okay. Um, so yeah, as we talked about before, the causal effect of interest that we want is the average treatment effect of the treated. Effect. Yeah, so the treatment effect on those who were treated. So, for example, it's going to be average because we're looking instead of just between one individual now, it's two groups. So we need to take the average effect among the group. And then we want the effect of receiving treatment, but only for the treated population because they're the group that receives treatment. And so to have a counterfactual group, we want a group that looks like them, that has similar characteristics, so that we can say they didn't go to the hospital, so this is what the treated group's outcome would look like if they didn't receive treatment either. And then we can compare those two groups. Okay. So now we'll talk about the counterfactual itself and what we need for it to be valid. And this is going to set us up for many different types of methodologies where we're trying to find that counterfactual. So this is just defining what we need for a counterfactual. And then in further chapters, we'll say different methodologies, trying to find the perfect counterfactual, which is going to be different in any situation or research. Okay, so as we said, having a selection bias will harm our estimates because it can understate the true effect of treatment. It can also overstate the true effect of treatment. It depends on the situation. So in this case, the hospital example, it might even change the treatment effect of going to a hospital from positive, so making people healthier, to negative because we're seeing sick people going to hospital. So then when we're comparing the two groups, we'll get a negative sign because the health of people that go to the hospital are lower than those that don't go to the hospital. So selection bias can really change our results, and it's not good for policy recommendation because, of course, we want to be estimating an accurate effect to reality. And if we're not doing that, we can't really inform policy decisions. Okay, so by being able to compare the differences in outcomes for one individual across the same moment in time would eliminate the selection bias problem. So we talked about this. If we had one individual in the same moment, let's say we cloned ourselves. So there's two Sandras here, and one of me goes to the hospital, and one of me doesn't go to the hospital. Then I know for sure that when I compare the outcomes, those are my for sure two potential outcomes. That's my Y1I and my Y0I. So going to the hospital, not going to the hospital. And we know there's no selection bias because I'm the very same person. But of course, that's impossible, right? So that would be the perfect scenario, but it's impossible. So this is known as the counterfactual problem, which we already kind of discussed, but formally the counterfactual problem is that we can only observe one state for any individual. They can either receive treatment or not, but never both in the same moment of time. Of course, you might say, yeah. Ay, what the heck? Zoom hates me today. It's not opening my chat. Stop it. Okay. I don't know why sometimes it works and sometimes it doesn't. A ver. If someone had just asked me a question, I cannot open it. So, oh wait, if I click on this. No, I don't know. Sorry. Ask me in voice if you have a question. Okay. So yeah, as you may think that, well, that's not true. We can observe two different outcomes for one person. We always have the person before they receive treatment and after they receive treatment. Do you guys think there's any problems with doing this? Anyone? what would be the problem with comparing one person, if they received a treatment, why can't we compare them before they received treatment to after they received treatment? What do you think? My God. No one? Okay, we'll talk about that right now, I think. Not quite. We'll talk about that in 5 minutes. If anyone has an answer before then, feel free to speak. Okay. Oh wait, we're talking about it right now. Never mind. I'm answering it right now. Okay, so even comparing one individual across 2 moments of time is not necessarily causal. So suppose we are comparing, as I said before, individual eyes health outcome before they go to the hospital versus after they go to the hospital. So the problem is that's not necessarily causal, because we cannot certainly know that the only thing that is changing in that time is them going to the hospital. So we cannot isolate for the effect of just going to the hospital. And that's because when you look at one person over time, other things might be changing as well. Maybe the individual decides to eat healthier in the same time, or they decide to exercise more, or maybe some other policy is implemented that has some other healthy initiative that also improves their health outside of them going to the hospital. So as we talked about before, the world is constantly changing. New policies are always being made. Different habits of an individual can change too. So when we want to compare one individual across time, we really need to be careful that that one thing is the only thing that's changing. And that's almost never the case. So that's why if you just run a regression saying, let's look at one individual and see how their health status changed before versus after they went to the hospital, that might not be valid. Okay, so if we can compare one individual across time or in the same moment of time, because that's impossible, how can we address the counterfactual problem? So what we want to do is use statistics. Statistics is our friend here. So when we have large enough sample sizes, you can find a treatment and control group that are statistically identical on average. So if we have a full list of characteristics, age, education, health status before, I don't know, I can't think of any others, but do you own a home? Are you married? All of these different characteristics, when we can find two groups that, although not each individual has exactly identical characteristics, on average, each characteristic could be statistically identical on average for both groups. Does that make sense? I'm not saying that each individual has to have perfectly identical characteristics in both groups. It's just that for this characteristic, say age, on average, it's 35 for treatment group and control group, something like that, right? And so statistically identical would be statistically significant at the whatever 5%, 1% level. Yeah. I still can't open my chat and it's freaking me out. Okay, anyways, any questions about this counterfactual problem? No, it's pretty logical. Okay, so then when we find this treatment group and control group that are statistically identical on average, then we can say that the average difference in outcomes is a causal effect of the treatment, because we know that they look exactly identical on average. So then any difference in the outcome between the treatment group and the control group can be attributed just to the treatment because nothing else differs between the two groups. So then there's no selection bias because they're identical on average. When they look the same, there's nothing different before, then you add a treatment to one group, the difference can be attributed to the treatment in the outcome. Yeah. Okay, so sounds easy, but it's actually pretty challenging. I'm sure you guys are realizing that as you continue through your thesis, if you're in your last year. But whatever the program is, whatever your methodology is, the main goal of any research to begin with should be finding a valid comparison group. It's extremely important, right? So it may not be perfect, but without a valid counterfactual, we don't have causality. Preguntas? Great. Okay, so we have some requirements of a counterfactual group to kind of ensure its validity. So these are what we have. The first requirement of a valid counterfactual group, or for a counterfactual group to be valid, is one, we already talked about this, that in the absence of the program, so before the program exists, so this could be considered our baseline or the before period, before treatment at all, we want our groups to look statistically identical on average. So I just spoke about this. So yeah, the two groups on average should look statistically identical in all characteristics, especially those that matter to our treatment. So whatever, of course, whenever we have an outcome variable, there's going to be some variables that are more relevant than others that could especially be affecting our outcome. So for example, if we want to know the effect of education on wages, so what's an extra year of education? How does that affect our salary? When we're looking at that relationship, you think what other characteristics or what other variables will be very important to affecting your wage, right? So other things might be ability, it might be experience, it might be age. So there's a lot of different variables that are more relevant than others that you want to be very careful and make sure that they're balanced between the two groups, that they're statistically identical. Because if you produce a research and you can't show that the two groups are balanced in characteristics that might also be affecting your outcome variable, your referees, which you guys are going to be referees later this semester, but your referees or the editor of paper will say, no, that's not acceptable, because then we can't know for sure that the effect is being driven by your X variable. Maybe it's all these other characteristics that are just different between the two groups. And then that's not a causal effect, that's a selection bias term. So that's why that's important, and it's definitely more relevant for the variables that you're concerned about the most affecting your outcome variable. Okay. And then the second requirement is that the treatment should not affect the comparison group either directly or indirectly. So this is called spillovers. So if the treatment is affecting the control group, for example, if somehow, even though the control group isn't supposed to receive treatment and it does receive treatment, what do you guys think can be the consequences? Anyone? Cuéntame.
It will affect the outcome, the result.
Yeah, it would affect the outcome because think about this. If we have a treatment that positively affects our treatment group, so they start here and then they get positively affected, but then the comparison group is also receiving some treatment, so then they're also positively affected, then that's not a valid comparison group, because remember that the comparison group is supposed to stay unaffected. So for it to be valid, they need to be completely unaffected by treatment. If they don't and they're somehow affected, then we're not going to estimate a true beta, because it will be understated, because while our treatment group's receiving a positive effect, so is our comparison group. And if our comparison group's receiving a positive effect, the true effect size is going to look smaller than it actually is. And if it looks smaller than it actually is, we'll think that the program is less effective than it actually is. And so maybe we won't recommend it as policy when it's actually a really good one to implement, but we're just not actually estimating a proper counterfactual, because somehow the counterfactual group or the control group is receiving treatment.
Hello, excuse me, there are some questions in the chat.
Oh yeah.
Can you see, please?
I can't open my chat, but wait, let me try. Oh, yeah, somehow it just worked. Okay, thank you. So, oh wow, we have a lot. I'm sorry, guys. Okay. So, the counterfactual relates to what we will never know. Yeah, so Giuliani asked about the counterfactual. We can never really observe the counterfactual, because the counterfactual is specifically the outcome that the treatment group would observe if they didn't get treated. But remember the counterfactual problem where you can only observe one outcome, so then they receive treatment. So we can never observe their Y0I, and therefore we need to estimate the Y0I, and we're estimating it using a completely different group, right? And so what we have to do then is say, okay, well, since we don't know the treatment group's Y0I, we need to estimate it. And to ensure that it's accurate, let's make sure that the two groups are identical on average. So then they must behave the same on average. So then our outcome Y0I will be effectively estimated by our control group. So we never observe the counterfactual of the treatment group. It's all about estimating for it using a control group. And to make sure that's accurate, we have to make sure that it looks as similar as possible to our treatment group. I don't know why. Okay. And then because the conditions when they weren't receiving versus receiving can change. Oh, this is about the, what was I asking? Conditions they weren't receiving. Was that about the selection bias? Okay. Sorry. What does it mean to say, in other words, the treatment effect should be the same for both groups? The treatment is not only for the treatment group? Yeah. So that's a good question. To say that the treatment effect should be the same for the two groups, only the treatment group receives treatment, right? Because the control group has to be completely absent of treatment, it receives nothing. But for it to be a valid counterfactual, we need to know that they are both responding the same way to treatment effects. So this is also an issue of external validity. If you guys know what external validity is, it's basically whether you can, I think we talked about it on chapter 1, but it's being able to find the effect for this treatment group and say it's true for other populations. So it's generalizable. We can use it for policy decisions because they would have followed parallel trends. Okay, wait. So they would have parallel trends, not necessarily. wait a minute. So, sorry guys. You just need to know that both the groups would respond similarly to treatment, or else it won't be a valid counterfactual, or it won't be a valid policy recommendation either, because then you can't say the effect for treatment is true for the control population and maybe not for populations in general. So then it's not actually useful. So we need to make sure that the both groups would respond similarly to treatment. And yeah, that's all I have to say about that, I believe. Okay. If the treatment is knowledge, is it more possible there will be spillovers like training? That's a good question, Santiago. So if you're receiving some information treatment, it's definitely more likely that there could be a spillover, especially there's a lot of information treatments in development papers. So maybe people are receiving information on how to have safe sex to prevent STDs or any diseases, or to prevent pregnancy. So maybe if I live in one household and I receive this information, I'm likely to share this information with women in nearby households. So there could be spillover there. And that might be unavoidable. There's always potential for spillover effects. And then we'll talk about this later in chapter 3. But a good way to get around that is to make sure the treatments at a larger level then. So instead of treating for the individual or the household, if we have an information treatment, we should put it at the village level or community level, because I'm more likely to talk to people that are my neighbors or in my community. But if the next village is 15 kilometers away and I only walk places, then I'm way less likely to share information with them. And so if we're treating at the village level, there is way less likely to be spillover effects. So these are things that we need to think of when we're setting up an experimental design, and try and be aware of what the potential spillover effects are and how to minimize it by maybe putting treatments at a larger level. Okay. Wouldn't it be better if you can prove the policy has spillovers? Oh, I see what you're saying, like positive effects. Okay, so of course, like when you're thinking of kind of externalities, like positive externalities we always want, because the social benefit is greater than just the one cost of treatment. So at a societal level, yes, spillovers would be good, if it's a positive treatment effect, which it normally is. But if we're interested in estimating the true effect, it's not good, because then we're contaminating the control group, and so the control group's receiving treatment. And then we're not going to get a true effect size. So if we know we have a treatment that has spillovers, sure, it's good as like a policy recommendation. We can say, we think this is really good because it doesn't only help the person that we give this treatment to, it helps their neighbors too, and the whole community is better off. That's great. But when you're estimating the effect, you need to make sure there's no spillovers, because then you won't accurately or estimate the effect, and that can actually be harmful for policy recommendation, because you're likely, if it's a positive treatment effect, you will understate the treatment effect, and then the policy is less likely to go through. So it's good in terms of social welfare, yes, but in terms of estimation, we do not want it. And it is possible to prove that there's spillovers. You can just normally you can know if the control group's receiving treatment by doing a survey afterwards. That's normally what economists do. So asking both the treatment and control group, oh, did you use the program, whatever it is? So did you receive the box of food for your children? Did they use it? Maybe there was bad organization in this program, so some control group houses actually receive the box of food. That's definitely possible. So just a survey can help you know who received the treatment, and then we shouldn't include these households in the program or in the analysis because they will contaminate our results or bias our results. Same in the treatment group. If some of the treatment group was supposed to receive treatment and then they don't for some reason, they also shouldn't be included in our estimation, because when we think they're getting a positive effect and they're not getting treated at all, that will also bias our estimate. Right? Any more questions? Right? Is it? Wow. Okay. So we do not want spillovers in this situation when we're trying to estimate an effect. And then third condition is that the outcomes of units in the control group, should change the same way as outcomes in the treatment group if both groups were given the program or not. So they should respond to treatment in the same way, which I was just responding to about recently. But that's the same thing, like even if they don't receive treatment. Can I repeat the first condition? Yes, I can, Deanna. The first condition or requirement, so that would be that the average characteristics of the treatment group and the control group should be identical in the absence of the program. Okay, so that means that they're identical across all characteristics on average. So for example, if I have a characteristic age, I take the average age for a treatment group and the average age of control group, and we want them to be statistically identical. That doesn't mean they have to be exactly 35, but it needs to be statistically significant. So if we did a difference test, it would need to be statistically significant at the 5% level, the 10% level, something like that. So for all important characteristics, they should be statistically identical, and that ensures that these groups are comparable and that there's no selection bias. This is really essential for removing the selection bias, because if, let's say, one group, if we're looking at the effect of education on wages, as we talked about before, and one group, the treatment group, has really high experience as well as higher education, then how can we say that it's the education affecting our wages? It might be a combination of education and experience. So that would be the selection bias. Is it an elementary? Is it an elementary characteristic to have the counterfactual? I'm not sure I understand. It's really important. Oh yeah, I see what you're saying. Yeah, it's one of the first most important steps of doing research, and it's definitely going to be one of the most challenging, because just like think of real life, how groups are really different than each other. So to find a group that is able to be a comparison can be really challenging. And they also have to kind of, if we're looking at the macro level, so for example, distritos in Peru, then they need to have similar economic shocks or be close enough that they have similar economies. And we know that in Peru, all of the coast is really different from the Sierra and from the Selva. So it's really hard to compare within Peru for that reason. It's very heterogeneous. So it's definitely a challenging part of the research process, is finding a counterfactual and showing why it's valid. Right? So these are kind of steps to show how it's valid. So You can always compare mean characteristics across the two groups and say, look, these are very comparable. So that would be an indication that they respond similar to treatment. So yeah, the third comment I was just talking about is really important actually, because notice how it says, is it paused? No. If both groups were given the program or not, they need to respond the same. So think about the or not. We need to be sure that even though the treatment end group and control group look similar to begin with, that the control group will respond to no treatment the same way as the treatment group would respond to no treatment, because that's going to be what we're estimating our counterfactual. And if our control group behaves differently than our treatment group moving towards the final outcome, then it's just not valid. We need to make sure that they would respond similarly or behave similarly. And usually economists argue that's true because their characteristics are similar, so they must behave similarly. The only really reasons that they wouldn't maybe would be cultural differences. But if you're looking within one country, that's not really relevant. So yeah, that one's easily, you can't test it, but you can just look within the context. There's no reason why they shouldn't behave differently. They're in the same geographic region, and yeah, that's all. Are there any questions about the requirements of a valid counterfactual group? No? Okay. So yeah, of course, when the above list is satisfied, we have the 3. Then we have a valid counterfactual group, and then any differences in the outcomes we can attribute to the program, or whatever the treatment is. Okay, so when we do not have a valid counterfactual group, the control group, which does not receive treatment, will be different from the treatment group in some way to begin with. And this is testable because we can look at descriptive statistics. We can look at just survey data, household data. Yeah. Okay, so we can always test whether the treatment group and the control group look similar. And that will be the basis for telling our reader that we have causality, which is what the economist is trying to do. We're always trying to show why our estimate matters and why we can show that it's true. So the more ways we can verify that and confirm that we have causality is the better. Okay, so when we have any differences in characteristics between the control group and the treatment group, we're concerned that our estimate's biased. And that bias will be an effect that we're measuring that we're currently attributing to our treatment effect, but it shouldn't be. So whatever direction the bias is going, upwards or downwards, the estimate is either too large or too small, and it may be even in the wrong direction if the bias is strong enough. So normally it will just change the magnitude, so how big our sample size, or sorry, not sample size, our estimate is. So maybe the true effect is 0.05, but when we have our selection bias, it goes up to 0.30. So that would be a difference in magnitude or size, but the signs can also change too. So we can estimate a positive effect when it's really negative. So yeah, whenever we have an invalid counterfactual group, our impact evaluation will not estimate the true impact of the program. Okay, and then there's two examples of counterfactuals that are not valid, but they're really tempting to use. We really want to use them, but we can't. So just be careful of these. So the first one is before and after comparisons. So we already talked about this a bit. You are not able to get a causal inference from using a before and after comparison. That's because while we're controlling for selection bias, right? We're not worried about selection bias because we're comparing against one person. So then we assume that their qualities are the same over time. But we're concerned about other things changing over time, such as the economy, maybe other policies, maybe, I don't know, other things change over time. Right. And then the second example is enrolled and not enrolled. So this is like a classic OLS example, I guess. Think of people who receive treatment versus people who don't in the same moment of time. So for example, so there's a program that individuals can choose to enroll into. There's a selection bias issue. That's because we're comparing two different groups of people, and they're going to choose whether they or not they receive treatment, and that's going to be determined by some underlying characteristics that we don't want to be affecting our outcome. So for example, health insurance, perhaps people who buy health insurance are sicker than those who don't on average. So it's the same thing as going to the hospital, and that would bias our results if we're looking at the effect on health, because our outcome variable to begin with is different between the two groups. So the first problem, the before and after, selection bias isn't an issue, but the fact that things change over time is. So time variant factors. And then the second one, enrolled versus not enrolled, selection bias is an issue. So that's time invariant factors, but they change their differences across individuals. I'll write that down. I'm going to write it into the chat. So time invariant changes. Okay. With that, let's take a break. We'll meet up at 6 p.m. 7 p.m. Okay. I'm gonna hide, but you guys can ask me questions. I'll be at my computer. All right, let's get started again. So for the next 20 minutes, we'll start on the readings, I believe, for this chapter. And then the last 20 minutes of class, we'll look at Stata so you guys can feel prepared for the assignment. All right? Entonces, okay, let's consider an example first of a bad counterfactual group before we get going into our papers. So consider an example where a training program for unemployed youth to help them enter the labor market. So it's just this program where they receive some training on really practical job skills so then they can find a job later. So assume that 2 years after the program has been launched, an evaluation attempts to estimate its impact on income by comparing the average incomes of a group of youth who chose to enroll in the program versus a group of youth who, even though they were eligible, chose to not enroll in the program. So the problem is when there's choice of whether you can enroll or not, there's always going to be selection bias because your choice of entering a program is based on some sort of characteristic or quality that you have about yourself. So maybe the people that do choose to enroll into the program are way more motivated than people who don't enroll, and they care more about their labor market outcomes. And so is that driving the effect of differences in outcomes, or is it the training program? That becomes the question. So yeah, assume that the results, the outcomes, show that the youth who chose to enroll in the program make twice as much as those who chose not to enroll. How should these results be interpreted? Well, in this case, the counterfactual estimated what we chose our counterfactual to be based on the incomes of individuals who decided to not enroll in the program. So you think that based on our observable characteristics, that our groups are identical. But these groups are probably very different. And as I said before, maybe it's unobservable characteristics that differ between the two groups. Why did these people that received treatment choose to enroll while the other group didn't choose to enroll? Because they both had the choice and they look similar based on observable characteristics. So then why would not everyone enroll? So there must be something different between them, right? Because they had the choice. This is the problem. So those individuals who chose to participate might be highly motivated to improve their outcomes, their livelihoods. They might be more motivated to find a better job, and they might have a higher return to training as it is. So maybe even these groups are different between unobservable characteristics, and maybe these two groups respond differently to treatment as it is. So Giuliani asked, how do you identify a good counterfactual for this example? Do you guys have any good ideas? This is exactly what we'll be talking about in the next few units. So if anyone has ideas now, I'd be very impressed. But if not, we'll get to it. Does anyone have any ideas? How would we find a good counterfactual when we have differences in unobservable characteristics? Randomization? Yeah, randomization is a good idea because when we randomize people across treatment and control groups, we can only see if their observable characteristics are randomized, right? We can only see what's observable, but we can assume that if a randomization is done well, not only are the observable characteristics randomized, the unobservable ones are randomized too. RCT basically, right? Yeah, RCT, same idea. Good. Other ones that you could do possibly would be like some sort of instrument variable strategy where you try and find some exogenous channel of entering the program. But we'll talk more about that too in chapter 4. But yeah, the RCT is definitely the most obvious solution to distributing unobservable characteristics across two groups. Okay. So yeah, that's the problem, is that when we have, say, motivation or ability or some other characteristics that we can't measure is different between two groups based on how they sort into treatment status, that's going to create bias. And it's likely going to mean that they would have had different labor market outcomes to begin with, regardless of this training program. That means that we're not estimating a causal effect in the end. Okay, any questions before we start this paper? Great, okay. So this paper by Shu and Anderson is about legal origin and female HIV. So it's really interesting the way she finds a comparison group, so we'll get into that. So I hope everyone knows what HIV is. It's like disease transferred through blood, I think, body fluids in general. And it's really serious. I think it can change into AIDS eventually. I'm not exactly sure. I'm not a scientist, but yeah, it's really dangerous. I think it's a lot more prevalent in the developing world than the developed world, and especially in Africa. Africa is the most prevalent area of AIDS, or HIV and AIDS, actually. So, yeah. So looking at the motivation, approximately 80% of all people that are tested positive, all women that are positive for HIV, live in sub-Saharan Africa. So that's crazy. Sub-Saharan Africa is like 10 countries. And so for 80% of all women in the world that are positive with HIV to be in Africa or sub-Saharan Africa is really, you can see it's a problem in this area. So also, interestingly, in sub-Saharan Africa, it's the only place in the world where women, more women than men have HIV. Oh, thank you. Uncurable STD leads to immunodeficiencies and death by common infections. That's a much more detailed description. Thank you. Okay, so yeah, unlike all other places in the world, in sub-Saharan Africa, the prevalence of HIV is higher for women than men. So adult women aged 15 to 49, not 1549, 15 to 49, are on average 3 times more likely than men to be infected. So for the younger cohort, aged 15 to 24, extramarital sexual activity is normal. Yes, Juliana, we'll talk about more why that's an issue in sub-Saharan Africa and why that could be causing higher rates of HIV in females than males. That's absolutely right. Okay. So it's normal everywhere, I think. So for the young cohort, age 15 to 24, women are as much as 8 times more likely to be HIV positive. So you can see how this issue for women is really concentrated especially among the younger population, than all adults in general. So for all adults from 15 to 49, women were only 3 times as more likely than men to have HIV, but specifically for 15 to 24-year-olds, it's 8 times as likely. So this problem is referred to the feminization of HIV and AIDS in sub-Saharan Africa. So it's not really a good thing because, I mean, women are disadvantaged in these areas to begin with. So the extreme prevalence of HIV is a serious problem, and it's an important policy question. Okay, so until this paper, economists really didn't understand what is causing this trend that women are so much more highly infected than men with HIV. Okay. So yeah, as Giuliani said, the vast majority of HIV infection in sub-Saharan Africa is through unprotected heterosexual contact or activities. Okay, so I'm sorry, I'm so immature. So multiple sexual partners, both between premarital and also extramarital sexual activity is really widely accepted in sub-Saharan Africa. So yeah, it's just more of a cultural norm there, I guess, that extramarital sexual activities is more common and acceptable in these parts. And then also another reason that the author argues is that there is compelling evidence or convincing evidence that male circumcision reduces the risk of HIV infections in men by approximately 60%, which is really large. And so in this area, it's not really. So interestingly, she says that rates of male HIV infection are particularly low in North and West Africa, where it's predominantly male or Muslim. So it's a Muslim area in the North and West Africa. So circumcision rates are high, and also this Muslim culture tends to be more monogamous and less preferential to external marital sex. So they're having less external sex and more circumcision. So they find a lot lower rates of HIV among Muslim populations in Africa. Yes, comparison in sub-Saharan Africa, there's almost no Muslims and also lower rates of circumcision. And they see really high rates of HIV. Okay, so according to the data in Central Africa, Sub-Saharan Africa, more than 80% of HIV positive women are infected through their spouse. So the new hypothesis argues that there's this new hypothesis that says maybe if we strengthen women's property and inheritance rights, that will prevent the spread of HIV and AIDS by giving women more economic independence, security, and empowerment in general. So if a woman has more control of her finances and assets, then maybe she has more control of a relationship that she's in as well. But so far, as interesting as this may seem, there's no causal relationship identified among economists between this female negotiating power or bargaining power, so how much power I have in a household to kind of negotiate with my spouse, and then female infection rates. So far they don't have a link between this negotiating power and HIV rates in Africa, and so she's kind of looking to do that. Okay. So she's going to use some variation in legal origins, which is really interesting. So in Africa, obviously, I hope everyone knows, a lot of African countries were colonized. And so these African countries adopted the legal system of their colonizers at the time of independence. So even though a lot of these countries are free now, obviously, they just, when they became an independent country, they kept the legal system of whatever country adopted them or colonized them. Sorry. Right? So then there's variation in the types of legal systems between African countries based on who came and colonized them historically. So there's two types of law that the author is going to be using for this analysis. So for the British colonies, they had a system called common law. And then other countries from other parts of Europe, such as France, Portugal, Spain, Italy, Belgium, they use civil law. And so there's really important differences between civil law and common law that are going to affect a woman's bargaining power in her household. So they're going to use these differences in a law structure to say how much bargaining power a woman has, and therefore we can compare differences in HIV rates. Right. We're not linking, someone asked if the development depends on their colonizers. I think so, but that's not the question we're asking right now. We're just interested in HIV patterns as a function of the legal system of their colonizers. So I'm sure economic outcomes are, of course, also affected by these differences in legal systems and property rights and female power, but right now we're only interested in the effect on HIV rates. Okay, so we have the two different legal systems, common law and civil law. And so a lot of papers already have demonstrated significant differences between common and civil law countries with regards to legal outcomes. So for example, civil law countries exhibit less secure property rights than do common law countries. So civil law has weaker property rights than common law. So maybe we think weaker property rights mean woman has less negotiating power, and then maybe we think that civil law countries have higher rates of HIV. And then on the common law side, common law is associated with lower formalism of judicial procedure and greater judicial independence. So basically, just there's the process of law is less formal than in common law than civil law. And these indicators are then in turn associated with better contract enforcement and greater security of property. So basically, the law is most relevant for women and for bargaining power in the household, especially in developing countries where marriage is almost universal. And so obviously, if marriage is really universal in developing countries, the most important laws will be marriage laws, not actually specifically marriage property laws, because that says how a woman is going to be able to have authority over her own property. Okay, so there's very important differences between marriage property laws between civil and common law systems. And they really start from how the law treats a household. So under common law, traditional common law, married woman practically has no legal rights. So basically the husband is considered the owner of all the household and all assets, and the woman is part of that household. So she's basically owned by the husband. Yes. Oh. not sure about the civil law and the common law. Right, so the common law stems from the British, and the civil law stems from French, Portuguese, Spain, Belgium, other European countries. And there's important differences between the two, but since we're only interested in the outcome HIV rates, and we think that HIV rates will be affected by women's negotiating power in a household, then we think that the most important laws will be how women can control her property rights. Civil law is what we have in Peru. I didn't know that. Okay, so yeah, it sucks. All legal systems suck, I'm pretty convinced. All right, so as we said, the laws most relevant to a woman's negotiating power will be how she can control assets and her household property. So under common law, which is the British system, a woman cannot administer her own property, even be part of a contract. She cannot conduct a business or even receive money earned from her labors. So the husbands were the sole owners of all property between the couple. So she was basically just working for her husband and she had no control of her money. Obviously that's changed, but we're just looking at the legal origins. And so how obviously in this situation, if she can't control whatever she earns, or she can't even be part of a contract or a business deal, she's going to have to rely on her husband a lot to be able to survive, right? She has no household power. She fully is dependent on her husband. In contrast, the other marital, so for the civil law, they had a system of community marital property. So that presumes joint ownership of all property during the marriage. So joint ownership means that the wife and the husband share ownership of whatever assets they have. And also, under the situation of divorce, it also protects the woman, basically equally splitting all marital property. So the civil law is obviously much better for women because it ensures that they have equal share of the assets. Therefore, they aren't dependent on their husbands because they know that they can, if they need to, they can leave the situation and still have half of whatever they shared together. Right? So it's a lot more equitable for women. Okay. So we can see how civil laws are a lot better than common laws for women in terms of household bargaining power. Okay, so let's look at the cause and effect question. We talked about this in chapter 1. It's basically your research question. So she asks, do formal laws that a woman's rights within the household, do the formal laws that change women's rights within the household, especially those related to marital rights, so how much rights she has as a wife, and how much of their assets or shared property that she can keep if they get divorced, how does that have an effect on female HIV infection rates? So she expects to find a positive relationship between common law and female HIV rates. So that's because areas that are common law, we saw women had less power in the household. So therefore, she expects that HIV rates will be higher because women can't protect themselves as much. And maybe that means that the husband's more likely to go have sex outside the marriage, or more likely to force her to have sex without protection, or other reasons. Yeah, so they can't really negotiate safe sex practices as well. and therefore they're more likely to be infected. Okay. So the author's using DHS data. It's like a health survey data set, and they have data on HIV. Obviously, it's important for this. And they're also using geographic data. So they want to compare women right beside a border. So let's say we have two bordering countries. One is civil, one is common law. So we want to look right around the border between the two countries of women, and find differences in HIV rates. And so the reason that she looks within one border, right on one border, is because she wants to compare within one ethnicity or one culture. So maybe there's some cultures that aren't contained in just one country. It's spread out across two countries near a border. Then we can control for the fact that there might be differences in some cultures or ethnicities that create differences in HIV rates based on cultural factors such as differences in acceptability, maybe of extramarital sex, something like that. All right, so basically it's looking at the ethnic groups. The larger the ethnic group, the more likely it is to be across two countries. So she finds that 51% of the sample, so approximately 157,000 women, fall into partitioned ethnic groups, so ethnic groups between two countries. And then within that group, 35% of the total sample, so 108,000 women, are in this ethnic group across two countries. Wait, partitioned ethnic women with different legal origins. Yeah, that's logical, no? Anyways. Oh, okay, I see what you're saying. Yeah, so there's some countries that are spread across, some ethnic groups spread across two countries, but maybe they're both civil, so we can't compare them. So we only want ethnic groups spread across two countries with two different legal systems. So that's the variation she's going to use. And then she argues that when you look within one ethnic group, characteristics are going to be very similar. The only difference should be that, on average, the legal system. Okay, so this is the map she used. Oops. So basically, this map 1 shows differences in HIV rates. You can see it's really intense in sub-Saharan Africa, here down south. And then this map, shows two different groups now. Civil law versus common law countries. So it's hard to tell the difference, but the slightly lighter shade is civil and the darker gray is common law. Okay, and then these are ones that border right next to each other. So a civil law country should be touching a common law country. And then within that, we have ethnic groups. Yeah, we have different ethnic groups. And so yeah, in this third panel, you can see how she only is keeping the variation of ethnic groups across the ethnic groups that go across two different countries so that she can compare within one. Any questions on that comparison? Okay. I'm actually going to stop this paper here and we'll finish it on Monday just because I want to show you guys for 15 minutes this data tutorial. I posted it on Figa, but just to show you in person, I think it might be helpful. I'm going to open up my data. Okay. You guys can see my screen, right? Okay, this is data. I'm sure you guys have all used it before. But just starting very basic here. This is the main screen you open. This is where you can write commands. So I can write all my commands here. I don't have any data yet, so that's my first thing I want to do. Okay, so I wrote everything in a do file, for example. So you can open a do file right here. You see it says new do file editor, and I can just click on that and it opens this page. And it's really nice because I can write things in this page. And so I can say, for example, change destination to whatever. And then here button, it says execute do. Maybe yours is in Spanish, so it's different, but you want to hit do and then it will run all the code you have. So it's really nice. I already made a do file, so we'll refer to that one, but that's how you start your own. And I really recommend it because if you don't do that, you're going to have to manually write in everything into the command section. And there's no way you can remember all your code, especially as you get more advanced, you're going to be running longer code. So you're going to want it to be replicatable so that you can run it multiple times and even send it to different people so that they can verify that it's correct. So that's why you always want to, even like so you don't forget, like just to remember what you wrote, always leave a do file and save it, and then you can just run it whenever you want. Okay, so first thing we need to do is import our data. So you can either go file, import data, and then it tells you asks you what kind of data you have. So yeah, you can do that. But I'm just going to show you what I wrote in my code because it's easier. So first thing you want to do is hit clear. I mean, right now it's fine. It doesn't matter because our data is clear, but say you already are running code and you already have data and code in your mains data. And then you want to start your do file from the beginning again. Make sure you hit clear or else you'll get an error. Okay, so when I want my data to read my data, it needs to know where it is. So I need to change destination, CD, and then wherever it is in your document, you can find it by right-clicking and checking its properties, and it will tell you where it's located right here, location. So that's how you can check where your data is. So I'm just going to change my destination to make sure we'll be able to read where my data is. And then you import your data. So in this case, it's a DTA file. So I just say use this data. If it's an Excel data, for example, or CSV, you'd have to go import CSV and then the name. So slightly different, but we just have a DTA file. So I imported it, and as you can see, all of my data is right here. Okay. So you can see all the variables are on the right side, and they all have kind of descriptions. So that's where we're at. Okay, so you can spend some time looking through your data. I always recommend doing that at first. So one thing I can do is hit sum, and sum will just summarize all my data for all variables. So it shows us the variable name, how many observations we have for it, the mean, the standard deviation, the min, and the max. That's just a nice way to look through all our data and make sure nothing looks weird, make sure variables are substantial enough. Some we can see this variable has 0, so we may as well drop it. If you want to clean your data, anything that has 0, you may as well drop and just clean your data. MS. Codebook is another way of looking through it. And it shows more, I believe, like it shows the type of data your variable's in. So for example, you can have numeric data, which is the most common, where your data is displayed in numbers, but you can also have a string variable where your data is not in numbers, it's in letters. So yeah, then it shows you different percentiles, the mean, the standard deviation too. If you have any missing data, right? So that's another way to look through it. And then also just browse. So browse, I can click here for data editor. I want to browse. So this shows me all of my data and all of the values. So as I'm looking through it, one nice thing is that you can see all of the missing data is as dots. It's just like a missing value. What would be bad if our missing values were some sort of number like 99. Sometimes authors clean their data like that, so a missing variable is number 99. Of course, you want to be aware of that because if we're running any sort of analysis, that's going to bias our estimate, not because of our research strategy, just because we didn't correctly address our missing values. Whew. Really hard to talk for 2 hours. Oh my god. Okay, so yeah, you can also browse your data just by typing BR or browse. That will bring you to this page that I'm just on now. And then another way to understand your data that I like to use is like graphs. So you can always, whenever you're trying to think of a graph to use or any kind of strategy, you can always go help, search, and then like graph, and then it can show you a bunch of different graphs that you can use. Wait a minute. Yeah, graph. This shows you a bunch of different figures, different plots. Scatter plot is a really common one to use. A two-way line graph, a pie chart. So I'm just going to show you an example. Graph pi will give you a pie graph, and I just chose variables that are within the same category. So for example, you can see this is basically data on a farmer. And the idea is that these farmers, this was a data for an experiment. So the papers, wait, where's my paper? The paper was called Impact of Village Savings and Loan Associations, Evidence from a Cluster Randomized Trial. So if you guys want, you can look it up. Basically, these farmers received this Village Saving and Loan Association program. So it was basically a saving mechanism. And the authors are interested in looking if this mechanism actually helps people's outcomes. So they looked at number of meals consumed per day, household expenditure, number of rooms in the dwellings. And so they basically wanted to know if the savings program actually helped people save and be able to improve their household outcomes. So that's what this is doing. So this is just some descriptive data, like what do these farmers use their land for? So for example, acres maize is how much area of your land you use for maize. For different crops, basically tobacco, rice, cotton. So all of these are different possibilities of land use for the farmer. So maybe we want to know what is the most common type of crop to grow. Then we can show that as a pie graph. So I just wrote pie, graph pie, and then all your variables that you want to compare. And I'll just run that. And so you can see how it makes a really nice pie chart. So that can be useful for showing descriptive statistics as well, because then we can say oh, well, clearly maize is the most popular crop, and the second most popular crop is this hybrid maize. So then that's an easier way to understand your data rather than just trying to read numbers, which can be challenging sometimes. Right? And then, so then the next important thing that you guys should know how to do is making summary tables. So basically a summary table will show whatever characteristics you want of variables. So normally I like to do this using this command called mean. And if you ever don't understand a command, always just search it, mean, and it will give you really specific instructions on how to write your command. So Stata can only read a command in this certain format how it defines it. So you need to make sure that when you're writing a command, you write it in the way that Stata can read it. So this is like the syntax page, and will give you instructions on how to write your code. You can see mean, so this is your command, mean, var list, that's all the list of variables that you want to include. And then you can include different conditions, so like an if condition, if you want to add a weight, and then all your options. So that's a pretty standard syntax for a command. And then all your different options are down below, and it gives you descriptions of what they are and how to use them. So for example, you can say over a certain variable list. So maybe I have a treatment variable and we want to compare between treatment group and control group. So you can say over treatment. So there's a lot of different options that goes into great depth. And then it stores results. That will be an ELIST, so you can always pull back your results. So now that we understand it better, I just chose some random variables, I'm pretty sure. Okay, so these are just household characteristic variables, like, let's find them. They were just here. So meals is the number of meals you had yesterday, number of months with fewer than 3 meals a day, household size, household age, the age of the head of the household, the education level, does the house have a cement floor, how much assets does the household have. All of these sort of things are demographic characteristics because it's trying to describe the household, right? So those are the variables I chose. I'm going to run this. I just wrote mean, all of these variables that I thought I'm interested in. I'm going to run that command. And so you can see how it gives us all the different means, standard deviations, and then also the confidence interval at the 5% level. So we have all these means, but say in my assignment I'm asking you guys to show me them. I don't want you guys to like copy and paste each number separately. That would take forever. Reasonably, if you're working for a job, they're going to ask you maybe to make, I don't know, 10 tables a week. So how are you gonna spend the rest of your life copying and pasting? Of course not. You need to learn how to export your data. So a good command would be outreg2. And so I say outreg2 using this table, and I want the table to be put in an Excel format. So I put this table .xls. You can also put it into a Word document. You can put it into text format, many different formats. You just need to look at the command. Outreg2 must be installed first. Yeah, I think so. I think it's like ssc install outreg2. You can also just go help outreg2. You can also go help outreg2, and then it will show you outreg, and then it can say, oh, do you want to install this, and just install it. So that as well. So make sure if you're making a table and you want to include different parts, first of all, we want to hit right replace, because that means if the table is already made with old estimates and we want to rerun it, this will replace our old table. And then I said stats, I only want to include the mean and standard deviation. And then I said sideways because I want them to be next to each other, not stacked on top of one another. So that's just for viewing purposes. Let's run those. So then you say, okay, here it is. This is the table it made. If it doesn't open here, it will also open in like your file, wherever your data is. So remember that my data, I said this is the location, this folder. So then the table will be put back in this folder. So you see it's there. And so this is the table it makes. It's really nice. Yeah. It just shows next to each other mean and standard deviations. If I didn't put the sideways in, the standard deviation would be under the mean. And so it'd be really long. So it's your preference. Okay. And then you can build onto the table too. So instead of replacing it, I put another line that says append. So then I do the same mean, except this time I make some if conditions. So I say, I only want to know the mean if the group is treatment and if post equals 0. So that means post is a dummy variable for the 2 time periods. So post equals 0 before treatment and equals 1 after. So I'm only interested in before treatment for the treatment group. And so I'll do the exact same thing except put append instead of replace, right? What is he doing? Okay. Then I'll do the same thing. Yes. So now you can see I have this extra column, and this is for specifically the treatment group. Okay, so this is for the full population. Oops. The first 2 columns, and then the 3 and 4 is for the treated population, specifically before treatment. And then the last thing you guys need to know how to do is run a regression. In this case, it's a randomization, so it's super simple. So for example, if we're interested on the fact of receiving this treatment, so it was a saving program, we want to know if it helps people eat more meals per day. So remember that we're only interested in post-treatment. We want to compare post-treatment for the treated versus not treated. So we say regress meals, treat is our independent variable, if post equals 1, because that's our after treatment. Right, so we get these results. This is what your results table look like. It tells you number of observations, your F statistic, R squared, adjusted R squared, all of that. And then the coefficient of interest will be this treat. So this is the effect of receiving treatment on meals, on the number of meals per day. And then it gives you your standard error and also p-value. So you can see it doesn't have a large effect, but it is significant, right? It's significant at the 10% level because p is 0.069. Okay, and then you can export those results in the same way using Outrig too. And then also, for example, this paper, they conducted randomization at a larger level. So they created blocks that they thought might affect different outcomes. So then we don't want to randomize among households, we want to randomize among blocks. So then we add this i.blocks, which basically creates a dummy variable for each different block. So you guys will be able to see. So treatment is still the variable of interest, but we're controlling for each block. So then we take away that variation from our treatment effect. So then all the blocks are included here as dummy variables, and we're left with our treatment effect of interest. Interestingly, we really don't get a difference in treatment effect, so doesn't seem that important. But yeah, you can export that in the same way using Outrig 2. There's also, you can also use STab is another way to export summary tables and results tables, so whichever you guys prefer. I think that's all I wanted to show you for today. And that's posted on CGUS, so you can refer back to it. Wait. Okay, so stop share. Do you guys have any questions about any of that? All right, well, I'm available over email at any time, so I'll be posting your assignment tomorrow. That will be due on April 26th at midnight over email. I want you guys to submit a Word or some sort of document with your answers to the question, as well as the tables in there as well. And then your code as well, send me your do file. Okay, so you should be sending me 2 things. Great. Okay, well guys, have a good night. I'll talk to you on Monday. Enjoy your weekend. If you have any questions, feel free to email me. Okay, end meeting. Bye everyone.